Good afternoon. Thank you for joining me on this video. I am Mr. Ish. We haven't talked about hyperbolic function limits, but today, fortunately for all of us, we will. And fortunately also in addition to the fact that we now have the background of derivatives in our minds, we have also looked at several videos on limits. So as we're progressing through these videos and now coming back to the topic of limits, it's going to be even more rewarding because we can see those types of questions we haven't seen before. Having the knowledge of derivatives will greatly assist us in some of the questions you might see in this video or in the next video. So without much further ado, let's get into this topic. We're going to start with this following question, and I've taken questions here from a textbook on single variable calculus, and I have adapted them for this video. So these will be all meaningful questions. If you're looking at this question, when we're looking at this right here, the hyperbolic sine function, and we have to try to determine the limit of this function as it approaches infinity, what is our function going to approach? If you remember very clearly, I've stated many times having graphs or access to graphs is the single best way to handle limits because you can easily look at the graph and derive your answer. If you just look at the basic function, hyperbolic sine function graph, if you just look at this graph, if you look at a graphing software and you look at it, it's going to look something like this. So just by looking at this graph, you can already come with your answer. And look over here, as x is approaching infinity, as x values are approaching infinity, and this by no means is indicating that it's turning inward. But when you're looking at the graph of hyperbolic sine function, you're looking at it looks something like a cubic function, but that's how it looks like. If you look at this, as x approaches infinity, as x values approach infinity, your function will approach very clearly, as you will see, infinity. You can just see that from your graph. The y values are going towards infinity as the x values are progressing towards infinity, and there you have it as your answer. But this is just a technique to have on the side by means of a graph, but most of the times we don't have a graph. So how do we challenge this if we didn't have the graph? And this is how you would think back to the basic definition of the hyperbolic sine function, and you would rewrite your question in that form. Look over here, is equal to e to the x minus e to the minus x over 2. Rewrite this without the negative exponent, e to the x minus 1 over e to the x over 2. Now look what happens. As x approaches infinity, this we're looking at right here, this part right over here, you get 1 over an increasingly large number, so large that it zeroes out, and you end up basically rewriting your function as this, and you can rewrite it again as this, e to the infinity over 2, because we kind of can substitute this over here, and you know e to the infinitely large number divided by 2 will make your whole function out of bounds, because you might as well say everything approaches infinity, and that is your answer over here, and it would be a good answer. Now the question has been modified. We're looking at limit of this function hyperbolic sine as x approaches minus infinity, and we have to see what this function approaches. If you again have the benefit of a graph, you can look over here. As x approaches the values of minus infinity, your function will approach, and you can see very clearly over here, your function will approach minus infinity, and that right there is the benefit of the graph. But we may not have the access to the graph, so we have to learn how to do this the other way. And again, I would recommend you to look at the basic definition of the hyperbolic sine and proceed from there. If hyperbolic sine function can be written as e to the x minus e to the minus x, and you can think back to the hyperbolic function video I presented, I talked about all of this. Now we're talking about all of this, but with the regards of limits. Now think about it. What is minus infinity? Minus infinity is the same thing as saying minus 1 times infinity. You can see that. If you take a minus 1, and I'm writing it right here, and you multiply by infinity, you've gotten a minus infinity, and that's how you want to look at this. Now look over here, what I'm going to do, show you a technique. The technique is this, and you can apply it as you want. If you take this minus 1 part right over here, and we multiply everything over here by a minus 1, but we're not applying the coefficients here by minus 1, we're applying here the x values by minus 1. See where you have x values, you're putting minus 1. Look what you get. You get e to the minus, and by minus 1 I mean like a minus x. You're doing x times minus 1, which is equal to a minus x. You're substituting minus x in place of x. That's what I meant to say. Now you have e to the minus x minus e to the minus x over 2. Open this up, what do you get? You get e to the minus x minus e to the x over 2. I've done nothing fancy over here. Now look over here. Apply the infinity in place of x. because we're talking about minus infinity as x approaches minus infinity. Now we've applied the minus and we've seen the effect of the minus. We've kind of flipped these things around, the exponents. Now we're applying the infinity portion of this minus infinity. Look what happens. You can write e to the minus x as, you can look over here, you can write all of this as 1 over e to the x minus e to the x over 2, right? Now we're at the step where we have to apply the infinity, and this is what you're getting, 1 over e to the infinity minus e to the infinity over 2. And you're thinking like we're supposed to be looking at minus infinity, but I've already applied the effect of that minus. Now we're just looking at the plain infinity, and you know what your answer is going to be over here. 1 over infinity zeroes out because the number becomes increasingly small, but you end up getting minus infinity divided by 2, which is an increasingly large negative number divided by 2, which is still a minus infinity, and that right there is your answer. And your answer for this will be a minus infinity, confirming what the graph shows you. As the x values approach here in the direction of minus infinity, your function will approach in the direction of minus infinity, exceeding beyond all bounds but in the direction of minus infinity. So this question has been done. So we switch gears now and switch over to hyperbolic tan function. If you have the basic hyperbolic tangent function, and I've never shown you graphs before, but I've talked about these hyperbolic functions, I never presented the graphs. But if you look at the graph of this hyperbolic tan function, you have asymptotes, horizontal asymptotes, y equals 1 and y equals minus 1. If you look at the actual graph, the graph looks something like this, the inverse tangent function. I'm just saying it looks like it, I'm not saying it is that, but this is what it looks like. If you look over here at your actual question, limit as x approaches infinity, this hyperbolic function will approach what value? And just by looking at the graph, as the x values approach infinity, in terms of the y, as I told you in the previous video, look at these answers in terms of the range. As you approach the direction of positive infinity, your function is approaching this asymptote, which represents the line y equals 1. So you can say your function approaches 1 and your answer would be right. But we have to learn how to do these questions without the benefit of the graph, because this is one of those methods where you may not have access to on a test. So how do you go about proceeding this? And this is how you're going to do it. You're going to break the hyperbolic tangent function into the hyperbolic sine divided by the hyperbolic cosine functions, and then you can write their definitions. Look over here, e to the x minus e to the minus x over 2, that's the hyperbolic sine divided by, now I'm putting the hyperbolic cosine function. Look over here, these 2's can cancel out, so essentially what you have left with is e to the x minus e to the minus x divided by e to the x plus e to the minus x. Now, what can you do over here? We can rewrite this without the negative exponents. Watch, e to the x minus 1 over e to the x divided by e to the x plus 1 over e to the x. And we have to look at this assumption here. Limit as x is approaching infinity, what can actually end up happening? Look at these terms over here, these 1 over terms. They become 1 over infinity become so increasingly small that you can cancel them out. You know this technique. You end up getting e to the x over e to the x, which cancels out because they're like terms, and you get 1, which corroborates and confirms what you have over here. So this is how mathematically and by use of assumption, this assumption over here, where you can zero out these terms, you can actually get the same answer as using the graph. Now this question is just in addition to the previous question. Here we're actually looking at how the function, same function, behaves as x approaches the values of minus infinity. Now you look at the graph again, as x values approach in the direction of minus infinity, in terms of the y, in terms of the range, look over here, as we are looking down in terms of the range values, this function is going to get ever close to this lower horizontal asymptote y equals minus 1, and you can say as these x values approach minus infinity, your range values will approach this horizontal asymptote, which is a minus 1, and this minus 1 will be your answer and you would be right. But that right here is by means of the graph. We don't want to become reliant on the graph, even though it's an excellent technique. The technique I want to employ over here is more mathematical in nature, and I will show you kind of like what we saw in the previous example with regards to the hyperbolic sine. But let's go with this. You break this up into its subsidiary functions. You have hyperbolic sine h x divided by hyperbolic cosine x, and you know you can do this just as I did very previously, and you can end up getting this. The 2's will cancel out, so I'm not even showing you this step. that step, but this is what you end up getting. Now we have to do the same sort of assumption as we did before. If you're looking at x is approaching minus infinity, we can view minus infinity as being a minus component, and it can be an infinity component. If we apply just a minus component here in places of these x's, look what we get. We can get here in the top e to the minus x minus e to the minus x, because we're kind of applying the minus component of this negative infinity, and then we get e to the minus x plus e to the minus x. When you simplify this out in terms of these negative signs, you get e to the minus x minus e to the x over e to the minus x plus e to the x. When you rewrite everything out, you can actually end up getting this. You can get 1 over e to the x minus e to the x. Remember, I'm just manipulating forms here, nothing more than that, plus e to the x. This right here has been rewritten in this form, and this right here is all the result of just applying, look over here, the minus component. I've only applied the minus component of this negative infinity. Now, from this form, if you actually apply the infinity component, you know what's going to happen. When you apply the infinity component, these 1 over e to the infinities will zero out, because they'll become increasingly close to 0 that you can zero them out. You essentially just end up having minus e to the x divided by e to the x, which are like terms with a minus on the top. When you cancel these out, you get a minus 1, and you're done. So you can see in this technique over here, like I did with the other question with the hyperbolic sign where x was approaching negative infinity, I separated the negative infinity into its two components, and I used each component separately in the form of this process. The negative affecting, and then playing around with these forms, and then the infinity affecting, and then giving us our final answer, which is corroborated by means of the graph. So this question is done. We switch gears now to the hyperbolic secant function, which is the inverse hyperbolic of cosine function. And we're looking at this question over here as x is approaching positive infinity. When you're looking at the graph of this function, you look at something which looks like this, where the x-axis, which is y equals 0, serves as a horizontal asymptote. The graph comes no higher than 0, 1. Now look over here. As x is approaching infinity, as x values are approaching infinity, your curve in terms of the y values or the range values is approaching this horizontal asymptote of y equals 0. And you know, based on the graph, if you're looking here in this direction, your function is going to approach 0, and that right there would be your answer. But we have to show this mathematically, because we can't always rely on the graph. Even though the graph is the best method, we can't rely on it in terms of exams and tests. So look over here. I want you to view this function as 1 over hyperbolic cosine function, because that's exactly what it is. And then bring in the hyperbolic cosine function definition, e to the minus x over 2. Flip things around, which you can. Fraction algebra, e to the x plus e to the minus x. Now look over here. Come down over here and rewrite everything without that negative exponent. You have 2 divided by e to the x plus 1 over e to the x. Now apply this x is approaching infinity assumption right over here in this, and you know you'll get 1 over infinity. It becomes so close to 0 that you can cancel that out. So what you end up having is this play out, 2 divided by e to the infinity, because x is a representation of what this is approaching, your a value. And you know this thing is going to be small number divided by such a large number that it might as well approach and become 0, and that will be your answer mathematically, corroborated by the answer derived from the graph. And then this question is done as well. The previous example that you just saw enticed me to present this one because I did not present it. So you see there's some slight changes here in terms of the lighting, in terms of the board, but let's proceed with this question. Previously we saw was as x was approaching infinity, but now look what happens as x is approaching 0 for this hyperbolic secant function. What value do we get as our limit? You know, if you're looking at the graph, whether you're approaching 0 from the right or if you're approaching 0 from the left, you know exactly the graph ends up and it peaks up right over here. So you can see it goes up to 1, but we want to show mathematically why and how this occurs. And you look at it again in terms of cosine. This is the hyperbolic cosine function, and you look at it in terms of its definition, e to the x plus e to the minus x over 2. simplify this into a more presentable form, e to the x plus e to the minus x, and that's what we're getting. You can again think about it now, look at it in this form. If you actually plugged in the value of 0 in places of these x's, though normally you could plug in values close to it, you could plug in values like 0.0001 or minus 0.0001, either way would be fine. But let's just go ahead and plug this 0 over here. You do 2 divided by e to the power 0 plus e to the power minus 0. You would really end up getting this 2 divided by e to the power 0 plus e to the power 0, because 0 is 0. It doesn't have the effect of a minus or plus. And you'd get 2 over 1 plus 1, and you'd get 2 over 2, and you'd get 1. And your question would corroborate exactly what you determined from your graph. So this was just an extra question I wanted to add to this video. Slightly different in terms of its ambiance and everything, but keep this in mind as this little video clip is incorporated into the existing video that you will see, and take note of this question specifically. It was an interesting question and I thought of it, so I'm adding it into the video. So now we have presented before us the hyperbolic cosecant function, which is the reciprocal of the hyperbolic sine function, and we have to determine where this function approaches as x approaches minus infinity. If you were to have the graph of this function, you would see something similar to like this. The x-axis and the y-axis are horizontal and vertical asymptotes respectively, and your graph will look something like this. If you're looking at this as x approaches minus infinity, look at these. You're looking at these minus infinity. You're approaching in this direction. What is your function approaching? Your function is approaching upwards right here towards 0. Right? Because this curve, this part of the curve in the negative infinity direction is trying to get as close as possible to this x-axis, which is really y equals 0, right? Your x-axis is y equals 0. Therefore, your function is trying to approach 0, and that 0 would be your answer. But we want to present this solution in another format, and I'm going to show you 2 ways of doing this mathematically. 2 ways. Let's look at the first way. If you look at a hyperbolic cosecant as this, the reciprocal of the hyperbolic sine, you can break it down into its definition components, and then you can manipulate that into this form right here, e to the minus x. Now look what happens. When you have come up to this form, you view minus infinity as being a derivative of 2 components. It's derived from a minus and is derived from an infinity. Now look over here, in this, from this definition over here, if you apply just the minus aspects, look what you get. You get 2 over e to the minus x minus e to the minus x. When you manipulate this, you get 2 over e to the minus x minus e to the x. When you manipulate this further, right, you can rewrite this in this other way, 2 over minus e to the x, and you don't have to even do it this way, plus e to the minus x. Now look over here. This e to the minus x is the same thing as looking at it as this way, 2 over minus e to the x plus 1 over e to the x. Now when you actually put in the infinite component or the infinity component, you get 2 over minus e to the infinity plus 1 over e to the infinity, which you know this value over here is going to be so small it will zero out. And then you're dividing 2 divided by a very large negative infinity component, or a 2 divided by a minus infinity is essentially what you're dividing it by. It's so arbitrarily close to 0, you might as well call it 0, because it doesn't matter if it's a positive infinity or a minus infinity. On either side of this 0, you're just at 0 pretty much, and you're confirming the fact that 0 is a good answer. This was just one way of doing it, using this approximation of using minus separately and then infinity separately. I want to show you another way of doing the same question right here, the other way of doing it, and I'll show you that. The other way of doing the same question is you start again with the assumption, well, it's not even an assumption, it's a fact, and you eventually come up to this form as I've shown you, minus e to the minus x. This is a form that you know how you can get. Now look over here, we'll do some algebra over here. 2 divided by e to the x minus 1 over e to the x, common denominator here. We're looking at this part of the denominator, and we have to get a common denominator within this denominator. This is what we get. We get e to the 2x minus 1 over e to the x. And you can see that I'm looking over here only and I'm doing a common denominator. 1 goes in e to the x times it multiplies with this, you get e to the 2x. Then you have the minus 1 over e to the x. Now flip this around, you get 2e to the x divided by e to the 2x minus 1. Now look over here, let's take the highest order variable or the highest degree variable and divide both the numerator and denominator with it. 2e to the x divided by the highest degree variable as e to the 2x. This is a technique I've shown you in some previous limit videos. E to the 2x minus 1 over e to the 2x. When you manipulate all of this, what are you going to get? On the top you'll get 2 over e to the x, and on the bottom you'll get e to the 2x divided by e to the 2x is a 1 minus 1 over e to the 2x. Now look over here. As you are making the assumption now, as x is approaching infinity, you will see changes occur over here. You'll get 2 divided by infinity because e to the x, e to the infinity is just saying infinity. And then you get 1 minus 1 divided by e to the infinity. Such a small number you might as well zero out. You basically get a 0 over 1 because this entire part over here transfers to the 0, because 2 divided by an increasingly large number is very close to a 0. You might as well call it a 0. 0 divided by this 1 is equal to a 0, and you confirm the fact that this function does approach 0. You've confirmed it in the previous way, now you've confirmed it in this way, and your question is done. And this process over here was no different than what I presented you in the original limit videos that we did prior to the derivative videos. The hyperbolic cotangent function is the last hyperbolic function we are looking at in terms of examples in this video, and its graph presented over here is kind of similar to that of the hyperbolic tangent in terms of the asymptotes. You have y equals 1 and you have y equals minus 1 asymptotes, the horizontal asymptotes. And when you look at the actual graph, the graph looks something like this, never going between this range of minus 1 to 1, but always stuck as a hyperbolic function on the way it is diagrammed over here between the y-axis and between these horizontal asymptotes. If you are looking at this graph over here, and you're looking at these two questions over here, as x approaches 0 from the right and as x approaches 0 from the left, we're basically looking at this 0 value from the right and 0 value from the left. You can tell exactly by the graph. When you're looking at x approaching 0 values from the right, your function is going exceedingly up out of bounds, and you know your answer is going to be positive infinity just by means of the graph interpretation, which is a very good way of doing it, and you would be right. When you're looking at it, 0 values, x values approaching 0 from the left, by means of the graph interpretation, your function decreases beyond bounds towards minus infinity, and you would be right. So these two answers are right, and your question would be done. But how would we support this? By means of a mathematical process. And for this specific question, let's use approximation. If you were to use a right side value close to 0, how about we do positive 0.0001, and we would have to plug it in here. Now you're thinking, what are we plugging it into? You would have to view your function like this: hyperbolic cosine divided by hyperbolic sine, and then you would have to bring in their definitions, e to the x plus e to the minus x over 2. The over 2's would cancel out, and e to the x minus e to the minus x, and this is the definition where you would plug these. You see this 0.001, you'd plug these in places of x, and then you'd see what you would get with increasingly smaller numbers closer to 0. And let's just run this number. We're going to run it to the denominator first, and we'll save that value, then we'll do the numerator next. If I'm running this 0.001 in this is what I get. I get 0.001 minus, and I'm going from the right side towards the left side, plus 0.001, and in my saved value for the denominator I get 1.999 times 10 to the minus 4, and I save this value. Now I run the same thing in the numerator from the right side towards the left side, positive 0.001 minus inverse of natural log just to get this, plus 0.001. These are all techniques you know how to do. In the numerator I get 2.0001, and you divide this by your saved value, and I get 10,000. I get 10,000 over here. Now what I'm seeing as I start adding more and more zeros over here, these numbers over here, these derived values will become larger and larger, so large that by means of approximation you'll get more and more zeros, and you might as well say you're approaching positive infinity. That's the right side. Approaching 0 from the right, you'll be getting a positive infinity. Now look at the left side approximation. You can use minus 0.001. Now you have to do the same technique. You'll take minus 0.001, run it through these x values and see what you get. And let's do it. 0.001 minus. I'm going to run it all and I'm going to present you an answer. In the denominator, I'm getting a minus 1.999 times 10 to the minus 4, and I'll save that. Now in the numerator, what do we get? Let's see. In the numerator, I get 2.000 and then a 1. I divide that by my denominator saved value, and I get a minus 10,000. See, a minus 10,000. So when we're doing the left side values, these negative values, I'm getting a minus 10,000. And you will see as you start increasing these approximations, getting closer and closer to 0, same thing with the right side and the left side, you get increasingly larger numbers, and you might as well say your limit or your function is approaching minus infinity, and your question would be done using both the graphical and using the mathematical techniques. Both the techniques are good, except this is a technique you need to learn basically, because you may have a test and you may not have access to a graphing tool. Now this question right here is our last question for this video, and we'll end with this hyperbolic function limit video with this. And you can see the graph still maintains and it stays the same. And if you just look at this question, as x is approaching infinity, this hyperbolic cotangent function will approach what value? You have nothing more to do other than rely on a graph over here. If you had a graph available, as x values approach the direction of positive infinity, your function is going to go along and traverse this horizontal asymptote of y equals 1, ever getting so close in this direction of infinity, so much so that you can say that your function will approach positive 1, and you would be right. The only thing we have now left to do is to show you mathematically why this is the case. Now I look over, if the question stated as x is approaching minus infinity, as x values were approaching minus infinity, you could also look at the graph and say your function is going to approach this y equals minus 1, this horizontal asymptote, which is a negative 1, and you could say in this case your function will approach a minus 1. But the question is talking about positive infinity, so that's what we have to focus on. And that'll be the only question we'll be focusing on right over here as our concluding question. And let's do this mathematically. How would you do this? You would use the definitions over here. You would break down hyperbolic cotangent into these children functions of theirs. You would plug in their terminologies or their formulas, e to the x plus e to the minus x over 2. You know the over 2's will cancel out. E to the x minus e to the minus x over 2. These cancel out by means of the fractional manipulation. Things cancel out like that. And all you're left with is e to the x plus e to the minus x, and this on the bottom. All you have to do over here is write this in a better way. E to the x plus 1 over e to the x divided by, that's the numerator representing the hyperbolic cosine, and the hyperbolic sine is represented here in the denominator, minus 1 over e to the x. Now as x approaches infinity, you know these values over here will zero out because you'll have 1 divided by such a large number that they're very close to infinity, and you end up getting e to the x over e to the x. Like terms can cancel out and give you that 1, which mirrors exactly what you're getting over here, and you're corroborating what you've determined mathematically by means of assumptions, and what you've determined graphically by means of the graph you have over here. So again, I will say graphing methods are usually the most reliable because you read exactly what you're seeing on the graph and you have your answer right there. So the graphing methods are the best, but assumptions are not too far behind, or all the other methods you've learned with regards to limits, and you have to learn how to use those assumptions and those procedures first, because graphing tools are not always available to you. But that'll be the end of this video, and I hope you enjoyed this video. And I hope you enjoyed the fact that I presented you the graphs of these hyperbolic functions, which I have not done so before, but now you have them before you. Keep this video in mind and the techniques I presented, and stay tuned, because in the next video I'm going to be talking about limits in a more enhanced way, but for the trigonometric functions. Stay tuned and have a good day.